what is the worst time complexity of the binary search tree for any operation? Anyone?
ON.
ON. Now, what can we do? See, what is the problem that do we have as some method with the help of which we can improve this property? Like as we have been discussing in the classes, that the in the binary search tree, when we are searching the what is the you can say we are doing any kind of operations, like when we are searching, it is the order of OH, right? The time complexity of the binary search tree is of the order of OH, where H is of the order of log of n, right? Because why it is of the order of log of n? Because at every point we say the search is divided into half. Because if we are searching for some operation, searching for some element, we start from the root node. So either we will be going left or we will be going right. We will not be traversing. We will not be searching throughout the tree. So only for the traversal we are going to do that. So in the worst case, we say the time complexity may be of the order of ON. Now, in order to handle this property, so that you can say we are just trying to make an effort. So can we do something that with the help of which, because the trees which are generated, see, where trees are generated randomly, so whatever data we have received, so it may be you can say it may be a skew tree, it may be a left skew tree, or it may be a right skew tree, right? So depending upon the input values that we have received. So in order to reduce that particular time, you can say in order to improve the worst case time complexity of the binary search trees, so what can be done? So there is an algorithm which can be used, which improves the worst case time complexity of the binary search trees, because the problem, see, the worst case time complexity arises in the binary search tree when they are totally unbalanced. So it may be a complete left tree or it may be a complete right tree, right? So in order to overcome such kind of problem, you can say three inventors, that is Edelson, Velsky, and Landis, they developed a new data structure that is called as AVL trees. And these AVL trees, they are basically called as the height balancing binary search trees. That means inherently they are binary search trees only, but to improve their worst case time complexity, some features, some new properties have been added. So what is that particular property that has been added in the AVL tree is that the height of the tree, that the height of the left and the right subtrees, that cannot have difference of more than 1. And this difference is called as the balance factor, or we can say the balancing factor. So that means at every point, whatever operations we are doing in the binary search tree, and if that operation increases the height, the difference in the height of the left and the right subtree, that means it becomes unbalanced. So in order to balance it again and make the difference between the heights of the left and the right subtree, we perform certain operations, and these operations are called as the rotations over here. So now we will see what are the various kinds of rotations we do, so that whenever after doing certain operations, like whenever we are inserting some data or we are deleting some data, right? So whenever we delete a node or we insert a node, the tree may get unbalanced. The height of the, you can say the difference in the heights of the left and the right subtree, that may be greater than 1. So in order to again make that difference, bring it back to 1, what we are going to do, we are going to apply certain operations, and which are called as the rotation techniques. So in order to balance itself, this AVL tree performs 4 kinds of rotations, and using any of these 4 kinds of rotations, you can balance any of the binary search tree that is getting unbalanced because of certain, maybe because of the insertion or maybe because of the deletion. So now we will see the examples of this one by one. So you can left rotation and right rotation. They are basically the single rotations, and then we have double rotations, that is first perform left, and then that means that is performed in a sequence. So first we perform the left rotation, then we form the right rotation, and in the second case we may be performing first right and then left. So using any of these rotations, So what do we do? So whenever we are creating a binary search tree, after insertion or deletion of every node, we are going to check over here. So that means that is an additional part of the lines of code you are going to add, and you will see what is the height of the left and the right subtree. If the difference in the height of the left and the right subtree is greater than 1, you will see what rotation has to be applied. So here you can say the first rotation, that is the left. So if a tree becomes, see, whenever you're doing some operation, you can check when a node is inserted into the right subtree of the right subtree. That means here you can see, so it becomes easy for you. So whenever you are doing some addition or deletion, so you check where this operation was formed, whether if this operation was performed into the right subtree of the right subtree. So here you can see the right subtree is to A to B is right, and then from B to C is also right. So here when we are, well, let's say we have inserted this node C over here, so that tree becomes unbalanced, because here you can see the difference becomes, difference in the height is greater than 1. So what do? We want to balance it. So what do we do for such kind of operations? So you can say for balancing such kind of trees, you can say for a subtree, you perform the left rotation. So that means insertion in the right subtree of the right subtree. So that means you have to rotate it left. So here you can see when we rotate it left, that means A becomes the child node of the B and the B becomes the parent node. And by performing this operation, now our tree is balanced. So next we have the right rotation. So the right rotation we perform when a node is inserted into the left subtree. So here you can, it is the left only, it is not right. Let me correct it right here, otherwise in this you will be forget about it. Okay. So in the right, when we perform the right rotation, when a node is inserted to the left subtree of the left subtree. So what we will do? We will rotate it right. When we rotate it right, B node, which was child of the C node, now it becomes a parent node of both the A as well as the C, and the tree becomes balanced. So you have to remember these situations, under what situations, under what scenarios you are going to perform the left rotation or the right rotation. And next we see the various scenarios under which we perform the left to left right rotation. That means we perform the double rotation. So there are 4 kinds of rotations. We can say there are different kinds of scenarios where we perform this kind of rotation. So a node has been inserted into the right of the left subtree. Here you can see now A is left child of C and B is right child of C. So a node is inserted into the right subtree of the left subtree. So this makes the C an unbalanced node. So these scenarios we will have to perform the left right rotation. So first left rotation that will be performed on the A. So that means now when we perform a left rotation, A becomes the child node of the B. So that means now you can say the new tree becomes CBA. Now it becomes, now you know this is left subtree, and whenever we have left subtree unbalanced, we perform a right rotation as we have seen earlier. So we are just performing the right rotation, so it gets balanced. So it means only the first step is new. The second step is already the old one that we have learned. So because now it is in the new state, and in this new state we can see that this is left unbalanced tree, the left child of the left subtree, that is making it unbalanced. So we just make a right rotation and then we are able to get the balanced tree. Similarly, the right left rotation, here you can see now the node has been inserted into the left subtree of the right subtree. So for C is the right node and B is the left child node. Now what do? We first perform the right rotation. So when we perform the right rotation, the complete tree becomes the right tree, right unbalanced tree. So what we did, what we learned in the single rotations, whenever it is a right unbalanced tree, we perform a left rotation. So here you can see in the fourth step, we perform a left rotation and we are finally able to get the balanced boundary tree. So these are the, you can say, this property that we have introduced in order to balance the binary search tree. So this is called as, you can say, this because of these new features that we have incorporated in order to improve the performance of the binary search trees, the worst case performance of the binary search trees. These are called as the AVL trees, right? So the binary search trees which have a balancing factor, they are called as the AVL search trees, and we do this balancing with the help of different kinds of rotations. So